right, let's look at example 2.2.4. I have two bases. I have 3, 2, and 1, 1. And I have basis C, which is -1, 2, and -2, 5. I want to find the transition matrix from B to C. All right, so I need, according to what we just learned, I need to take each of the elements of my original basis and write them in terms of the new one. So I'm going to have to write 3, 2 in terms of C, and I'm going to have to write 1, 1 in terms of C. All right, so let me do it just below. I need to write 3, 2 as a linear combination of -1, 2 plus A2 -2, 5. That means I need to reduce -1, 2 -2, 5 with constants 3, 2, and I'm going to get 1, 0, 0, 1 -19, 8. And so A1 is -19, A2 is 8. And so my first column will be -19, 8. All right, we do the same thing for 1, 1. We're going to get same coefficient but different constants. And when I reduce it, I'm going to get -7, 3. And so A1 in this case is -7, A2 is 3, -7, 3. All right, and so this is the transition matrix. Let me check something. Yeah, let's just note, I mean, I'm going to add it here. I'm mentioning it in the takeaway, but let's say it here. If I actually reduced, I mean, this is the coefficient matrix for both. So I can actually do both. If I reduced this matrix with my first and my second constants all at once, if I reduce it, I'm going to get both answers at once. Oh, sorry, I forgot to reduce the coefficient. This is what I would get. And so you don't need to do two separate steps. You could do just a single one, and you're going to get whatever's here. That's going to be your transition matrix. All right, so you put your the basis, the new basis, and the old one, and this is going to be your P from the old to the new. All right, I'll say it in the takeaway below. All right, so I'm assuming that I already know the coordinate vector for W in terms of B. I want the coordinate vector in terms of C. So what we have is if I want the coordinate vector in terms of C, I'm going to multiply the coordinate vector in terms of B by this transition matrix. So we've already found the transition matrix, and I'm going to multiply by 4, 3. I've computed it's a bit horrible numbers, but it's -97 and 41. All right, let's try a different problem. Let's say I know that the vector of C is -1, 5. I want to know how I can get the vector of B. All right, so we have that the vector of C is the matrix times the vector of B. And so the matrix will be invertible. So if I want the vector of B, I'm going to take PB of C inverse WC. I'm just going to take this and invert it and send it to the other side. And so here, the inverse of this matrix is 1 over the determinant. So the determinant is minus 3 times 19, that's 57, plus 56. So it's just minus 1. And then I'm going to switch the diagonal entries. So this is the formula from linear 1. And then take a minus to the other ones. And then I'm going to multiply them by minus 1, 5. And what I got is minus 32, 87. All right, but notice that we would have, let me put it in orange above, what we know is that usually this would be the transition from P to B. All right, so let's write what we've just learned in the takeaway. So the transition from C to B, this map, is just the inverse of the transition from B to C. And if V is Rn, like it was in the last case, you have a shortcut to find the transition matrix for B to C. Like I said here, you put the new and you put the old. So the new is C, the old is B. You reduce, you will get IM because C is a basis. And then whatever's on the right of it, that's going to be the transition matrix from B to C. All right, so that's a shortcut. It works only in Rn. The construction works on any vector space. So we'll look at examples that are not in Rn in the next video.